Hi, I'm Nick Moffat with Verisurf Software. Today I'll show you how to use the Creaform HandyPROBE to align, inspect, build, analyze, and reverse engineer parts and assemblies. The HandyPROBE is a portable optical CMM that offers a number of unique features. The system uses a C-track sensor and wireless probe for ease of measurement. The measuring volume is greater than a 12-foot arm, but with a similar accuracy. The target volume is between that of arms and laser trackers. Self-calibration can be performed on-site using a certified artifact for optimal accuracy. The C-track supports probing with the HandyPROBE as well as scanning with the optional MetraScan. Finally, dynamic referencing compensates for part movement to help maintain accuracy in a shop environment. We'll see an example of that later. Verisurf takes full advantage of all the data from the HandyPROBE and the MetraScan, points, point clouds, and dynamic reference information to enable model-based definition, 3D inspection and layout, and reverse engineering using Verisurf's many CAD tools. We'll look at that next. Verisurf's metrology software is built on a CAD platform, giving us full CAD design capabilities. CAD is required for reverse engineering, but it's also very helpful when inspecting complex parts. For example, we can analyze the model, we can pull dimensions from the model, we can even manipulate the model. In addition, CAD tools such as attributes, colors, and levels allow us to manipulate large part assemblies. Verisurf integrates design, inspection, layout, analysis, and reverse engineering all into a single application. Finally, Verisurf is designed for both model and print-based workflows. I'll continue by loading a model of our demo part. Verisurf reads all popular CAD files, CATIA, NX, ProE, etc., in their native format. This helps avoid the limitations of neutral formats like STEP and IGES, which Verisurf can also read. When we open a native file, Verisurf saves it in the MCX format and leaves the original file intact. All the data, including the model, measurements, analyses, and reports, are saved in a single MCX file to simplify handling and prevent data loss. I'll choose the MCX format and open our demo part file. The part is in place and the model is loaded. In the next step, we'll align the HandyPROBE. After we load a model, we typically align the device to the part so we can get real-time feedback on tolerance condition. We'll use auto-align since it's the easiest way to align to a model. We start by creating alignment targets on the model to control the orientation of the part. I'll choose Create Targets and place alignment targets on the top, front, and side of the model. I'll then choose Run Auto-Align and measure the targets as they're highlighted. After the final target is measured, Verisurf aligns the device using a best fit and displays the results dialog. We can review the results and modify the fit if necessary, but since the results look good, we'll choose to accept. When we do, Verisurf runs Inspect Build mode so we can verify the alignment. The small deviations indicate a good fit between the part and the model, which indicates that the alignment is correct. This final check validates the auto-align workflow since it shows that we had the right part, the right model, and we didn't make any measurement mistakes. Auto-align is a very powerful alignment tool, but it's simple enough for beginners to use. Plus, the results are easily verified using Inspect Build. The HandyPROBE is now aligned to the part. In the next step, we'll check surface profile. In the previous step, we used Inspect Build to verify our device alignment. Inspect Build is a special measuring mode that displays in real time the deviations between a part and the corresponding features in a CAD model. When we're inspecting a part, the deviation reflects the material condition. When we're moving a part into position, the deviation shows us how far to move and the arrow indicates the direction. Since the HandyPROBE is already aligned to the part, when we check profile, we'll assume the deviations are due to machining errors in the part. I'll start by measuring points on the top in single point mode. Notice how the deviations are represented with an arrow and deviation text. I'll switch to continuous mode and scan deviations around the part. When I press Escape, VeriSurf creates an analysis object in the data tree. If I highlight the analysis object, we can see the distribution of deviations in the color bar. If I double-click the analysis, we can change the way the deviations are displayed. For example, we can add borders to the deviation text. We can change the lines to spheres. And if we enable Use MBD Tolerance, VeriSurf analyzes the data to the corresponding surface callouts. Otherwise, it uses the global profile tolerance. I'll restore the original display, choose OK, and then add balloons to annotate the deviations. I'll choose Auto Add Balloons, apply to the limits, and save. Then I'll highlight the analysis object and create a report. I prefer to have the screenshot on top, so I'll change the order. I'll also change the logo. Select the Creaform logo. Choose OK. We can output the results in a variety of formats, including Excel, PDF, Word, etc. I prefer PDF, so we'll leave it there. When we create the report, we see the annotated screenshot, we see the Creaform logo, and we see the details in the body of the report. We've just seen how to use real-time deviation analysis to check profile. Next, we'll use it to position the demo part. If we know anything about metrology, we know the part has to remain fixed relative to the device. If either the part or the device moves, we have to rerun the alignment. The HandyPROBE eliminates this problem by tracking the part in real time using the cameras on the C-track sensor. We refer to this as dynamic referencing. If I place reference targets on the part, the alignment is restored automatically. In practice, we could simply hot glue or otherwise fasten the targets to the part. Anyone familiar with articulating arms or laser trackers will realize that dynamic referencing simplifies or eliminates the need to leapfrog. Since we're going to use build mode to position the part in the next step, I need to remove the targets. When we use build mode to position a part, we assume the form of the part is good and the deviations are due to errors in the position of the part. We refer to this use of real-time deviation analysis as build mode because it's often used to build fixtures and assemblies, but we can use it anytime we want to position an object in 3D space. We'd normally start by aligning the device to the basis of the CAD model by measuring features with known CAD values. We'd then position objects by moving them using build mode into their nominal location. Since the HandyPROBE is still aligned to the model, and since we moved the part in the last operation, I'll simply use build mode to move it back into its original position. I'll select and build to the circles first, since that's a quick way of getting the part located. I'll place the probe in the hole and move in the direction of the arrow. As soon as I'm close, I'll cancel the circle selection, enable MBD, and then build to surfaces. We've enabled Use MBD Tolerance so we can use Surface Profile to control the build tolerance. In other words, as long as the surface is located within the profile tolerance, we'll consider that the part's in the right location. There's always a tendency to want to build to 0, but as long as we build to green, the part is located in tolerance. Okay, this is much closer than I need to be for this step because we want to leave the part out for our next operation. This is a very simple example of the build process. Setting a complex part in 3 dimensions is much more complicated, but the process is essentially the same. The part is now located roughly where we want it to be. In fact, we'll move it out a little bit more because we want it misaligned for our next step. We've used inspect mode to check our part in real time. In the next step, we'll perform a similar analysis, but we'll start by measuring a point cloud. I'll begin by running inspect mode to check our device alignment. We know the part is good because we've already inspected it, and we know the alignment should be out because we left it that way intentionally at the end of our build demo. I'll switch to point collection and scan the part. We're not getting real-time deviation analysis. We're just collecting raw probe center data. When I'm done measuring, I'll press Escape and choose the Analysis tab. I'll highlight the clouds and choose the Analyze button. The results are similar to what we saw in Inspect mode, but the deviations are much larger because of our intentional misalignment. I'll hide the analysis object, select the clouds, and run Best Fit. First, I'll analyze the data for a baseline analysis, and then run the fit. When the fit is complete, the results show the part is good, similar to what we saw in Inspect mode. I'll choose OK to accept the alignment. If I toggle between the before and after best fit analysis, we can see the improvement. And if I select the Measure tab and run Inspect mode, we can see from the deviations that the best fit is applied to the device alignment as well. Inspect mode, which we saw earlier, and analysis, which we just performed, are very powerful tools for model-based inspection. In the next step, we'll measure and analyze prismatic features. All of the workflows we've seen so far have been model-based. We've aligned to a model, we've inspected and analyzed to a model, and we've built to a model. Next, we'll discuss print-based inspection and reporting of prismatic features. I'll align to the part frame shown here, but since we're not using a model, I'll open a new file. I'll start by measuring a plane and 2 lines for an alignment. Next, I'll run feature align. We can see the origin is located at the intersection of the 2 lines, so the data is aligned correctly. If I place the probe at the origin, we can see the device is aligned as well. I'll continue by measuring features starting with a circle. Next, I'll measure a sphere. And then a slot. I'll switch to continuous mode and scan the inside of a cylinder. I'll continue by measuring the partial hole pattern in single point mode. I'll switch to point mode and measure the left and right planes. I'll measure the left plane as 4 points. And I'll switch to continuous mode and scan the right plane. I can then fit the 4 points to a plane, and I can do the same with the point cloud. All of the features we've measured are displayed in the data tree. If I select a feature, I can see its characteristics such as position, form, and size. If I select 2 features such as 2 points, I can see the distance between them. And if I select 2 features such as planes, I can see the angle and distance between them. We've seen how the HandyPROBE measures prismatic geometry. Next, we'll see how to analyze and report the results. We briefly saw the report manager when we reported our inspection results. Next, we'll take a closer look as we analyze and report our prismatic features. For the report, I'll highlight the circles in the 2 end planes. When I choose the Reports button, the features are displayed in the Report Manager. If I highlight a feature, I can see its characteristics in the Details pane. We can use these fields to enter the nominal and tolerance values. I'll enter the nominals for Circle 1 so we can report its position. The toolbars allow us to add CAD features, to construct features, and to add GD&T callouts. I'll use the toolbar to construct the plane and then the circle through the hole pattern. I'll select the 4 circles and then choose Construct Plane. With the circle still highlighted, I'll choose Construct Circle to find the center. I'll then construct lines from the center to circles 2 and 3. I can highlight the lines, calculate the angle between them, and enter the nominal value. I'll construct the distance from the center to circle 2 and then enter its nominal value. I can select the end planes and calculate their parallelism, and I can highlight the center and circle 1 to find their concentricity. Finally, I'll report the position of circle 1. For the report, I only want the final values, so I'll highlight them before I create the PDF file. As before, we see the Creaform logo and the details in the body of the report. This is a very simple report, but it shows the use of constructions in GD&T. I referred to the measurement, analysis, and reporting of prismatic features as a print-based workflow, but it works equally well, if not better, with a model. For our next example, we'll look at a simple application of reverse engineering. Verisurf's reverse engineering tools allow mixed modeling using prismatic features, meshes, and NURB surfaces. Moreover, we can take advantage of the many CAD tools inside Verisurf. For this demo, I'll scan and then surface the contour on the top of the demo part. I'll start by scanning the part in continuous mode. When the measurements are complete, I'll choose the Reverse tab, highlight the cloud, and choose Patch. The fit parameters allow us to control the accuracy and the complexity of the surface. I'll verify the probe offset and choose Create Surface. When the results are displayed, we can see the values are in range, so the surface looks good and we'll accept it. We now have a surface that the parameters indicate is good, but how can we verify it? On the Measure tab, we can run Inspect and see how well the surface matches the part. On the Analysis tab, we can highlight the cloud and analyze it to the surface. The data from the HandyPROBE is traceable, so we have a way of proving the accuracy of our surfaces. This is a very powerful capability of an integrated metrology platform. This was a very simple example, but it shows how easy it is to create and to verify CAD surfaces. That concludes the demonstration. I hope I've given you a good appreciation for how Verisurf metrology software enables the Creaform HandyPROBE with a complete set of tools for model-based alignment, inspection, layout, analysis, and reverse engineering. For more information or to schedule a demonstration, please call us at 888-713-7201 or email us at sales@verisurf.com.